Hi everyone, welcome to the last video of this week, and in this video we will learn about multivariate missingness. Remember that when we learn about regression and imputation and stochastic regression imputation, we put ourselves in the context where only one variable had missing values, and obviously most often we have missing values in more than one variable, and the question is, what should we do in this case? And this is specifically for regression imputation type of approaches, because for mean imputation, if I have several variables with missing values, I just compute the mean of each of the variables and replace the missing values. And complete case analysis, it's similar, right? We just remove the individuals with missing values in the variables and we go ahead. Okay, so basically what should we do when we want to do stochastic regression imputation? For instance, we have seen that it's one of the best approaches to deal with missing values, and we have missing values in more than one variable. Well, in a very specific case, in the case where we have a monotone pattern, we can use the the univariate techniques that we have learned in a sequential manner. And let us consider this specific example. I have four variables, y1 up to y4, and five individuals, and I see that I have a monotone pattern of missing values, and one possible approach is to impute the missing values in y2 using y1, then imputing the missing values in y3 using y2 and y1, and finally imputing the missing values in y4 using y1, y2, and y3. So if we are interested in stochastic regression imputation, I will use, when imputing y2 using y1, y2 is my response and y1 is my covariate. Then when I'm imputing the values for y3, y3 is my response and y1 and y2 are my covariates. And similarly, when imputing the values in y4, y4 is my response and y1, y2, and y3 are my covariates. And that's it for a monotone pattern. We can use what we have learned before in a sequentially manner, or in a sequential manner, sorry. Well, when we do not have a no monotone pattern, there are two popular approaches: joint model imputation and fully conditional specification. Let us look at each of them separately, and let us start with joint model imputation. Well, in joint model imputation, what we do is to fit a multivariate model to all the variables that have missing values, and so it's kind of a generalization of what we have done before. And let us think of the concrete example where we have p variables, say y1 up to yp, and let us further suppose that y1, y2, and y3 are only partially observed, and y4 up to yp are fully observed. So what I could do under a joint model imputation is to specify a multivariate model for y1, y2, and y3 given y star, where y star here comprises y4 up to yp. So before we specified a univariate regression model because we only had one variable with missing values. Here, under the joint model imputation, I specify a multivariate model for the collection of variables that have missing values, and my covariates will be the observed variables, the fully observed variables. And the main drawback of this joint model approach is that it's not always, or most of the time, it is not trivial to set up a reasonable multivariate regression model, because if we have many variables with missing values, our multivariate model, its dimension, will be quite high. And in practice, most of the time, multivariate normal or T regression models are used for continuous variables. And when the variables are discrete, the variables that have missing values, when they are discrete, multinomial distribution is used. If we have mixed variables, say variables with missing values, and some variables are continuous and some others are discrete, then things are a little bit more complicated, but models do exist for fitting such or yeah, for fitting models for such type of situation. And yeah, the positive point about joint model imputation is tricky. We will not be looking at it. I'm just mentioning that it's one of the possible approaches, and in fact was one of the earliest approaches. And there are several packages, and these packages are in the context of multivariate imputation, not single imputation, but well, single imputation is a particular case of multivariate imputation. We are just imputing ons. So it's okay, we can still use these packages. And norm was the first package proposed for joint model imputation. It uses normal distributions, and then we have cat for when the variables having missing values are discrete or categorical. Mix when we have situation when we are in the case where variables having missing values are both continuous and discrete. So this package can deal with or as functions to deal with such situation. And then JOMO and Joint AI. It's a very recent package, and yeah, they all fit different types of joint models for imputing values when we have several variables with missing values and the pattern of missing data is non-monotone. Okay, so, but as I have said, I'm just mentioning this approach. We will not be using it. And another approach that was proposed later is the so-called fully conditional specification, or also known in the literature by multiple imputation by chained equations, or MICE. And later in the course, when learning about multiple imputation, we will be using the package MICE that stands exactly for this, multiple imputation by chained equations, quite a lot. And under this approach, the fully conditional specification, we impute multivariate missing data on a variable by variable basis. And if we go back to our example, or to the example that we have used to illustrate the joint model imputation, let's suppose again that we have three variables that are subject to missingness, and all the others, y4 up to yp, encoded in y star, they are fully observed. So remember that for the joint model imputation, we would specify a multivariate model for these three variables given all the other observed variables. Here, under the fully conditional specification, I look at variable by variable. So I specify a model for y1 given y2, y3, and y2 and y3, they have missing values, and y star that has all the variables that are fully observed. Then I specify a model for y2 given y1, y3, and y star, and similarly a model for y3 given y1, y2, and y star. So I'm not using multivariate models. All these models are univariate, right? I only have one response for each of them. And for instance, if y1 is continuous, I can choose a linear regression model. If y2 is binary, I might use a logistic regression. So here it's also simpler, right? Because for, as I've said, for the joint model, if the variables with missing values, if they are both continuous and categorical or discrete, then the model is much harder here, because I specify the model for each of the variables. It's easier because I can use univariate models, and we are much more comfortable with univariate models than with multivariate with a potential Ig dimension. So here the context is simpler, okay? And sorry, So how does the fully conditional specification works for this specific example, but it can be generalized to the case where we have more variables with missing values. So I remember that remember that I'm specifying a model for y1 and I'm conditioning in y star, which is okay because these variables are fully observed, but y2 and y3, they have missing values, and the same y1 and y3 have missing values, and y1 and y2. So what the fully conditional specification does is, okay, as an initial step, I will impute the missing values in y1, y2, and y3 by some crude method. For instance, I can use mean imputation, or I can randomly sample from the observed values to replace the missing values, like the plain OTEC approach. Then I have the three variables that are complete, but of course I've just draw, or I've just used mean imputation, so this is not satisfactory. But what I will do is then I will use the model that I have specified for y1, and I condition on y2, y3, and y star, and now y2 and y3 are fully observed, and so I fit my model using the observed values for y1. Remember that for stochastic regression imputation, for instance, we were only using the observed set of data, so I'm only using the individuals with observed values for y1, and I'm using the values of y2 corresponding to those with observed values on y1, and these y2 values, they might be a collection of both observed and imputed values, the same for y3, and y star is fully observed. And then I do the same for y2. I fit my model that I have specified for y2, given y1 observed and imputed, y3 observed and imputed, and y star, they are all observed. Then the same for y3, and I need to do this several times, right? Because I'm just I'm in the first step, I'm doing some naive type of imputation using mean imputation or random draws, and then I fit my models, and I need to do this several times for several iterations until some convergence criterion is met. And right now we will not look at this convergence criteria. There are several of them that can be applied, because later when learning about multiple imputation, we will look at this in detail. Right now I'm just mentioning the approach that is nowadays preferred when we have several variables with missing values. And okay, once I have looped over the iterations and imputed values for y1, y2, and y3, sorry, the values that I have imputed for each of the variables in the last iteration, they will then be used to replace the missing values in the original data set. Okay, so summarizing, for the joint model, we specify a multivariate model for the variables that have missing values, and for the fully conditional specification, also known as multiple imputation by chained equation, because we do a kind of chain over the different models, I specify a univariate model for each of the variables that contain missing values, and and the models are conditional on the fully observed variables and also on the variables that have missing values. And that's why in this initial step we do some naive imputation, and then we need to iterate to guarantee that in fact our imputations are stable, and that I'm not imputing just values that in fact they don't make much sense. Okay, and just to make the point, and as I have just said, the major advantage of the fully conditional specification is that a sequence of univariate regression models is way easier to understand and also to implement in practice than a multivariate regression model. But there is a theoretical issue with fully conditional specification, and the issue is that there is no guarantee that the algorithm draws imputations from a well-defined joint multivariate model, right? We are using univariate conditional models, and we do not know if the corresponding joint multivariate model is well defined, but there is some recent work, for instance, from Hughes et al. And co-authors in 2014, and there are also some other works, and these authors, they have identified conditions when in fact the fully conditional specification approach, when the draws that we obtain under this approach, they come from a well-defined joint multivariate model, and the key condition is that the conditional models are compatible, and by compatibility, the authors mean that there exist multivariate distributions whose conditionals are those specified in the fully conditional specification, like the univariate models that we specify. This is a bit technical, and as I've said, we will not look at this right now, but when going to multiple imputation, or when learning about multiple imputation, we will look in all of these in more detail. Right now, I just wanted to tell you how we should proceed when we have several variables with missing values. And that is everything for this week. See you on Tuesday, or online or on campus. Thank you.